Hi. Hi, everyone. Welcome to today's reset. We're really happy to have Luciano Pomatto, who's going to present the cost of information. And we have two panelists. We have David Walker-Jones and Jeffrey Mensch, who will make it more lively. We don't have any co-authors today, so if you have a question, you can either also unmute yourself during the talk, or you can wait until the discussion time after the talk to ask your question. So Luciano, the screen is yours.
Thank you very much for inviting me. And thank you for being here in one capacity or another. So today I'm excited to tell you about a paper some of you may have seen at some point. And it is a joint project with Philipp Strack at Yale and with my friend and colleague Omer Tamuz. So what do we do in this paper? In this paper, we want to understand a certain number of issues related to modern information economics. So it is fair to say that the idea of treating information as a commodity is by now fairly standard in economic theory, and much of modern economic theory is in fact built on this idea, the idea that information is a good that is valuable and is scarce. When we want to think about representing information as a commodity in a way perhaps analogous to the way we model other commodities in our models, there are a number of few key questions that come to mind. I mean, the most basic one is probably how to represent information. How to measure its value is another natural question. But the one I want to focus on today is how to model the cost of acquiring information. How to represent this cost in a way that is convenient and amenable to analysis. Let me just put this a little bit into context. The way we represent information as a commodity, by far and large, fits into the framework that was given to us by Bodenbluth, Shapley, Sherman, and Blackwell. So we have an unknown state of the world that represents some variable that the decision maker, or more decision makers in our model care about. And an experiment is this good that produces information, right? So an experiment is usually modeled as a collection of probability distributions, one for each state I, taking values over this set S of signal realization. So here the intuition, the interpretation is standard. If I is a true state, then mu I is a random mechanism that produces outputs, a signal realization. So standard examples are, for instance, the case where we have a binary state, we are flipping a coin, and the coin is a little bit biased, so they provide some information in case the state is 1 versus 0. Another classic example is one where we perform a measurement subject to some normally distributed noise of a state that can take value -1 and 1. How can we model the cost of acquiring or producing information? So with a lot of simplification, let me try to summarize 3 different approaches that we find in economics regarding to this question. The first one is the simplest, conceptually simplest one, perhaps, is to look at some parametric family of experiments. So here the argument goes, the agent can acquire information through a signal that is, say, normally distributed with a certain variance and a mean equal to the true state, at a cost that increases as we decrease the variance of the signal, right? So this is a very intuitive model. We see variations of this in information economics. Another approach to this is that of having a detailed model of information acquisition. So tell me, what are the actions that the decision maker can or will take to acquire information, and what are the costs involved? And then we're going to solve for the optimal information acquisition strategy. So in this regard, a classic example is the model of Wald on sequential sampling, where the decision maker can decide how many sample points to do, how many samples to draw from a population, and then there is a cost involved for each sample that is drawn. So these two approaches are classical, right, and go back to the 30s, 40s, and 50s. But more recently, there has been another approach to model information acquisition, which is also quite well known by now and goes under the name of rational inattention or flexible information acquisition. So here, the basic premise is that the information acquisition process is non-parametric. So the decision maker has access to basically any possible experiment. So the decision maker can, in principle, decide to acquire a perfectly informative experiment or any possible variation of it. The cost of this information acquisition step is described by something that is, in principle, very general, right? Is just some functional over experiment, some cost function defined over experiment. Here, of course, the difficulty is that the space of experiment is very large. So then the question becomes, what is a good cost function that we can use to model this cost? And following seems most of the literature, maybe less nowadays, but traditionally most of the literature has taken this cost function to be equal to the reduction in entropy of the decision maker's beliefs. Okay, let me.
Luciano,
yes.
Luciano, just make sure I have the notation right. So when you're writing this curly E as like a set of experiments,
yes,
you're defining this as a distribution over posteriors, right?
I'll be more formal in a second, but
because otherwise you need to include like the prior in there, because that's definitely an element of what's going into the reduction of entropy costs.
Oh, very good. Yes. So when we're going to, so E, this calligraphic E is going to be in the paper and in the presentation is going to be just experiments without a prior. And but to use the entropy cost, you need some prior. So that has to be also that you can take that as to be part of the cost function. Notationally, of course. This approach based on mutual information has seen many applications of interest, but for all of its merits, raises some important questions. Let me just to fix idea, let me tell you formally what this model looks like. There is a decision maker who is solving some decision problem under uncertainty, so we have a set of states, a set of actions, all of this is standard. But then the decision maker will acquire some information at a cost that is formalized as in this equation at the top. So what is this, right? So this function H is negative of Shannon's entropy. So Shannon's entropy is this, one could describe it as a measure of randomness that goes back to information theory and Chris Shannon's work. We have a prior Q over the set of states. The experiments, the information that we're acquiring leads to a posterior belief that is random, and so has a distribution that is denoted here by pi mu. Is the distribution of a posterior belief induced by the experiment and the prior. And what is this cost measuring? It's measuring the variation, the expected variation in the entropy of the decision maker's belief, variation between the ex ante prior and the ex post posterior, right? So here the idea is that an experiment that is more informative will, on average, lead to a bigger change in the randomness of the prior, comparing before and after receiving information. And of course, the idea being that a posterior that has lower entropy describes a less random, lower entropy has a less random distribution, so there is more information in there. And the way this is plugged in a decision problem is through this equation that you find, this optimization problem that you find at the bottom. The decision maker maximizes overall possible distribution over posterior beliefs consistent with the prior. Given the posterior P, the decision maker would choose the optimal action, and the decision maker solves this benefit cost calculation, taking into account that there is this cost C of choosing any particular posterior, random posterior mu. Actually, mu here is an experiment, sorry, not pi mu is a distribution of posterior beliefs, but the idea is hopefully clear. Okay, so what are the key challenges of this model? Without thinking too much about any specific properties of the functional form, there should be something that should immediately come to mind, which is the fact that there is only one single parameter in this model, which is this coefficient kappa that multiplies this expression. So the idea being that when this parameter goes up, the cost is uniformly larger, but it is striking that this functional form has only one single dimensional parameter. So then the question, of course, is how rigid is this model? If you think about preferences, for example, even when we think about very parametric functional form like Cobb-Douglas, we usually expect to see, right, a number of parameters that is larger than one. So it is known that this rigidity leads to a number of conceptual and practical difficulties when you try to use this model. When certainly not the first ones to point this out, it is known, for instance, that this cost function has troubles when you try to capture the fact that certain states are harder to distinguish than others, right? So this is a well-known difficulty. And in fact, both panelists have done work on this. Another property that we're going to think about today is that it has built in a notion of decreasing marginal cost. So let me leave this here for now, and it will be more clear once we get back to our action paper. So what do? We start from the following simple intuition. So when we look back at standard commodities, one way to study cost functions in, say, productions is to categorize cost function in terms of decreasing, increasing, or constant marginal costs, right? And maybe the last case, the case of constant marginal costs, is perhaps the conceptually simplest one. So in this paper, as a starting point, we try to characterize cost function over experiments that displays some notion of constant marginal cost. And it may not be exactly clear what do we mean by this idea of constant marginal cost. It certainly wasn't too clear for us as well. So to make this intuition precise, we're going to take some kind of axiomatic approach. So we're going to use axioms to characterize a new cost function over experiments. Now, these axioms, I personally don't think of them in the same way I think about axioms, say, in a standard decision theory paper, nor in the way I think about axioms when reading a paper in social choice or social welfare. So we're not trying to argue that these axioms contain any grain of rationality, or they have any sort of normative appeal, or that they can be useful for doing a revealed preference analysis. We think of this axiom as something that is useful to us being people who want to write a model with costly information acquisition. They're useful in the sense that they hopefully capture some properties of this cost function that can be are easy to interpret, right? And it should be make it easier to understand what we are assuming. A main contribution will be to characterize and study a new family of cost function over experiments that capture this idea of constant marginal costs. Let me skip this. Let me skip this for now, the related literature, and move right away into the model. So the framework is the classical framework of Blackwell on comparison of experiments. So we have a set of states. An experiment is a tuple of distributions, distributions indexed by the state. So the idea here is that if true state is I, if the value, maybe that the quantity of interest stakes is equal to I, then we're going to see some realization of this random mechanism where mu I is a distribution over signal realizations. The idea being that mu I is the true distribution over signals when I is the true state. These measures are assumed to be mutually absolutely continuous. And this will be important for our model so that what we are ruling out are situations where you can perfectly learn the state, or you can perfectly learn that a certain state is not the true one. So in our model, there is always going to be some lingering randomness left. A quantity that will play an important role is the log likelihood ratio between two states when we see a signal realization S, right? So this is just a ratio of the densities. So of course, when this log likelihood ratio between I and J is large, conditional on seeing the realization S, we should have higher confidence in I rather than J being the true state. A cost function is a function defined over experiments, and calligraphic E here represents the set, or I mean more formally the class of all experiments. And we look at experiments where the measures are mutually absolutely continuous, and also where the moments, this log likelihood, the moments of the log likelihood ratios are finite, right? So this rules out certain experiments where the distribution of the log likelihood ratios are very, very fat tails, but it captures basically 99% of what we have seen in the literature. So the ingredients are standard, but then the question is, what does a cost function or defined over this large set look like? So to arrive at the cost function that we're going to discuss in this paper, we start from a number of axioms, properties, right, that will pin down a particular type of cost function. The first one is really standard. It says that increasing the informativeness of an experiment should decrease its cost. So if we have two experiments, mu and nu, where mu dominates nu in the Blackwell order, then the cost of mu should be higher. Remember, the Blackwell order says that mu dominates nu if I can always basically reproduce nu by observing the realization of the signal mu and adding noise to it. In this sense, this is a sort of a free disposal assumption. So if I can produce the experiment nu from mu plus noise, nu should cost less. The second property that we impose on the cost function, the second property that we investigate, is something that goes at the heart of our approach, right? It's trying to capture some notion of constant marginal costs. So the sort of thought experiment about experiments, and I want you to think, is that of performing two different experiments that are independent, conditional on the state. So imagine I have two possible experiments, mu and nu. Think of them as sampling from two different statistical populations. I can take a sample from population 1, or I can take a sample from population 2. And now I want to think about the joint experiment where I'm taking samples from both populations, random samples. So this product, mu product nu, is the joint experiment where, conditional on the state, I see independent signal realizations. An example here, in fact, is that of drawing independent samples from two populations, but you can think also of flipping the same coin multiple times to learn about the bias of the coin, or to observe randomly fluctuating process for a longer period of time, all these kind of examples. Our key assumption is that our cost is additive with respect to independent experiments. This is what we take as a notion of constant marginal cost. The cost of adding nu to an experiment mu is constant.
So I think this gets back to my first question in terms of how we're defining experiments. So here we're defining experiments as conditional probabilities, right?
Yes.
So these mu's are not posterior beliefs. They are the probability of getting a particular signal given the true state of the world. Okay.
Yes, that's correct. That's the approach we take. This is an interesting issue, right? Where should priors be, right? When we think about the cost of acquiring information, and I'm sure you have more to say on this than probably I have, or we have in the paper. So when you think about the cost of entropy, the cost given by entropy, the classical cost function you use in these models, that cost is something that depends on the prior of the decision maker who's performing the experiment, right? I need the prior to compute the reduction in entropy of the decision maker's beliefs, to compute the cost function. Here, the prior doesn't appear in this formulation, right? An experiment is not something that depends on the prior, and the cost here doesn't include it. So when we start to work, this is not exactly something it's not my most recent paper. When we started to work on this, we were really confused by this aspect of the literature and rational inattention. Why is it that the prior of the person who is performing an experiment, so acquiring information, should affect the cost? Meaning, right, the cost of sampling a population, the cost of tossing a coin, the cost of performing a measurement shouldn't depend on whether I'm optimistic or pessimistic about the state, right? To me, this seemed like something a bit unnatural about the classical model of SIMS. And this is why we take this cost to be something that does not include the prior.
Right.
Now, when you think a bit more about this issue, then you can also think about situations where the prior perhaps should play a role. Think, for example, about a situation where I have this coin that gives me some information about the state, and I decide to flip it until I get enough heads, right, that I'm confident that the state is 1 and not 0. So when you have this sort of optimal stopping ingredient, when in the back of the model there is an optimization over when to stop, then you will see that the expected cost of performing this experiment, this compound experiment, now will depend on the prior. Even though maybe the action of flipping the coin or performing a measurement is something that is not depending on the prior, when you look at the expected cost, because the stopping time is decided by the decision maker, these expected costs should depend on the prior. So in the paper, what do? We have a first step which is the one, the first part, which is the one I'm describing to you here, where we don't include the prior in the model, right? In the second part of the paper, we have a small section where we say, well, suppose that the cost has the prior in it, right? So suppose that the prior is part of this cost function. Then, this gives you a more general model where the cost depends on two arguments. And then you can ask, okay, now how does the idea of constant marginal cost interact with the prior of the decision maker? And then we have a generalization of what we do. But there are then now, I think, at least two papers, right? There's more, but at least two papers that I think go deeper into this issue of prior dependence of the cost function. So there is one by Alex Blödel and Weijie Zhong, where they take seriously this idea that the cost may involve an element of stopping time, and so should be prior dependent. If you think about it as a reduced form model of the decision, a dynamic model, and they characterize cost function that do or do not capture this idea, and their prior dependence is really explored in interesting ways. Another paper is the recent paper by Tommaso Denti, Massimo Marinacci, and Aldo Rustichini, that it's a methodological paper about the relation between cost-dependent and cost-independent functions. So this is still sort of a not completely solved issue in the literature, at least to my reading of it. One way I interpret the model of this paper is one where the easiest way for me to interpret the model I'm telling you about is one where there is a decision maker who is not performing a stop in time, but rather decides how many experiments, how many copies to acquire today of certain experiments or different independent experiments. And this cost involves some physical action, some actual cost of sampling, measuring, performing an actual experiment in a lab that are not dependent on the prior. That's the easiest way for me to interpret this model. If the cost does instead depend on the prior, that to me sounds like a model that is a cost function that is a reduced form way of capturing stopping time problem. That's a way for me to organize the thoughts about this issue, but maybe there is more to be said on this. Any more comments? Or thoughts? Okay, so this is really our key assumption, and in fact, I think it would be interesting to understand just what these two assumptions imply: additivity and Blackwell monotonicity. We have an answer for the case of two states. So if you look at the paper, and you dig deep in the appendix towards the very end, if you're still awake, you will find that result. But we don't know what these only two basic conditions imply for when you have more than two states. The third axiom is sort of a bit of linearity axiom. The idea is the following: imagine that you have experiments that generate information with some probability, but with the remaining probability do not. So given an experiment mu, we call the diluted experiment alpha mu an experiment where with probability alpha you perform mu, with probability 1 minus alpha you see an uninformative signal. So you have sort of like a faulty machine that sometimes does work and outputs for you a signal realization with some information about the state, and which sometimes does not work, and you know it's not working, and you see this uninformative signal O that tells you, okay, I have to run it again if I want to see anything useful. So what we assume is that the cost of such an experiment is linear in the probability of success alpha. So this is another way in which the cost of information that we look at is additive, it's linear. Right? So we have different ways to think about this assumption. One way to think of it is that this assumption is implied by another assumption that is very standard in the literature, which is posterior separability. So if you're not familiar with it, it's a type of linearity that is very convenient for thinking about the cost of information, and it implies this property. Another way to think of it is the following. Imagine you have our axiom 2. So the cost of multiple IID copies of an experiment is linear in the number of experiments. Now imagine that we have, say, a coin, right, that we're flipping, and we decide, this coin or this experiment is a diluted experiment. So sometimes when you flip the coins or when you pull the lever, you get some information, sometimes you don't. And now imagine running these faulty experiments until we see a first useful realization. So now this seems to contradict what I said, right? This is a sort of a stopping time problem, but it's not something that involves the prior, because whether or not the experiment works has nothing to do with the state of the world. So imagine now this compound experiment where we keep pulling the lever until finally I see something useful. And you can ask, what is the expected cost to run this compound experiment? This expected cost, right, should be 1 over A times the cost of running the experiment mu once. So if you have axiom 2 and you think of the cost of this, then that means that the cost of this compound experiment is 1 over alpha times the cost of mu. And then what you would like is a cost function where there are no arbitrage opportunity, where running a diluted experiment should cost less or no less or more than running this compounded experiment. That's another way to think about this assumption.
Luciano, can I ask a question?
Yes.
How should I interpret these axioms? In the way I would have thought, like, you would ask some agent, do you prefer this experiment or that experiment? Questions like that. And then from there somehow, come up with this linearity, for example, that it's like you're revealing that the cost to you of running this faulty experiment is linear in the probability of the fault or something like that. So it's like it's some sort of whereas here and that seems like it to me, I don't know whether the question makes sense, but it seems like to me that would depend on how you're going to use the information too. So how should I interpret these axioms in terms of like behavior?
Very good. So the way I interpret these axioms as being not about behavior, but being about modeling, meaning when I look at something like entropy, I don't know exactly what we're assuming about the underlying technology for information production. I see a very useful functional form, capture something intuitive, but I don't know what are the economic assumptions that we are making. So I think about these axioms just as trying to basically write down an assumption of constant marginal costs. What makes it non-trivial here is the domain, right? When we write constant marginal cost for cost functions in our first year grad classes, right? It's just one definition, it's one line. Everyone understands what that means, right? And then we can move on. You don't need to call that an axiom, it's just a definition. Here we want to do something similar, but I don't know, there is no one obvious definition to write. These axioms are sort of our best attempt. So maybe the word axiom here is misleading because it's sort of leading, right, the mind to think of decision theory and an agent and trying to understand through the revealed behavior, the revealed answer to our questions, what is really going on in their information acquisition process. The way I think about this properties or axioms just as a way to express in the simplest possible terms and hopefully in clear terms what is that we're assuming. So these are axioms that are for us, right? For us who are looking at the paper, looking at the model, right? They're not axioms that try to be convincing, right?
But I guess it's something about technology that's what you're saying. This is like some properties of the technology that generates the information.
Yeah, the way I think of this is you want to write a model that uses information acquisition, right? For some context. And now you may say, okay, what if I use this cost function? Then the question for you, one question for you would be, does this idea of constant marginal cost make sense? Or maybe the context of the model is one where there are important fixed costs. If there are important fixed costs, then clearly this is not the right model. If you think that the agent may get quickly tired of performing multiple experiments, too cognitively demanding, that also may be not if that's a salient aspect of the model, this is not the right assumption. But you need somehow some axioms, some properties that are clearly stated to make these arguments, right? So these axioms to me are something that it's useful for organized discussion. So this is what this model is assuming. Do you like it or not? Is this useful for what you're doing or not, right? When you look at entropy, it's less clear because all I see is this object, this sort of idea coming from information theory. It's less obvious. Another way to do it, to think about cost function, which is along the lines you're saying, it's certainly also interesting, right? Is to say, look, I don't know what the cost function is. Let me ask, is the behavior that the model implied reasonable or not, right? And then what you're looking at are axioms over the random behavior of the decision maker. That's an approach that you find in a number of papers by Kaplan and Dean, also by my co-author on another paper, Tommaso Denti. That's also a very interesting approach, right? Maybe the two are complementary, but that's not the one that what we do here. At least that's how I think about it.
Thanks.
But I'm happy to chat more on this.
I see Francesco Squintani is raising his hand. Do you want to ask a question?
Yeah, hi. I'm Luciano. Nice meeting you. This is a great paper, first of all. I just wanted to say one thing. I mean, to me, it seems like, I mean, you're right, maybe these should not be called axioms, but these are very reasonable assumptions because this is what is often used in specific models of information where you think about costly information acquisition. So this type of assumption pops out in many papers going back to Taviani, 2001. The assumptions in which you toss a coin and you pay a cost, the same cost for every experiment you make comes up in a number of papers where you think about behavioral cost or even information acquisition. To me, I agree with you, what is bizarre about entropy is the fact that the cost depends on the prior. So to the extent that you want to give some structure to the idea that the cost should not depend on the prior, one possibility would be to back up what you're doing by saying, look, I mean, these are commonly adopted modeling techniques to talk about information acquisition. We want to make them precise and make them fit in a whole framework. We want to understand beyond the examples if there is a way to understand what costly information acquisition is. And so this is the way I think about it. So I wouldn't call them axioms. I would literally start with the fact that, look, I mean, this is the way it has been done. And if we want to understand deeply what this entails in a unified manner, then we have to go further from the examples. The other one is a small point. I mean, in a beta Bernoulli model, while it is true that you can think about every experiment, and you can think about the cost of each of the experiment being constant, but it is true that as you keep on adding experiments, the effect that the realizations have, for example, on the expected value is decreasing. So in that sense, the value of extra information goes down. So I would be a bit careful about the terminology of marginal decrease in marginal constant value of information, because there is this sense. You see what I mean, right?
Yeah, I see.
In a beta Bernoulli model, the expected value is L plus 1 over N plus 2. N is the number of experiments, L is the number of ones. So if you perform a larger number of experiments, the impact of an extra 1 or 0 goes down on the expected value. So this is just a small terminological issue I would be, because if you say that this is a way to think about linearity and constant marginal value of information, the effect that this has given a prior doesn't need to be linear.
Right. So yes, definitely, the value and cost of it are totally different objects in a way, right? So not just in the beta, but I'm sure in any sort of Bayesian model, you're going to have eventually decreasing marginal effects of the information on your expected values.
It is possible to write counterexamples, but they're very contrived. So you're essentially correct. I mean, if you search it on the literature, you find examples, but they're very contrived. So
that's interesting. That's interesting. I don't know. Didn't know.
If you do a search now, but you see what I mean, right? If you talk about constant marginal value, constant marginal cost, I mean, it is true. An experiment has a very real meaning, a literal interpretation of the beta Bernoulli model. But because our models are metaphors, then
no, yeah, it is important that surely to distinguish between cost and value of information. So, right. So, and this goes back to your first comment, which I totally agree with. Two models that are sort of special examples of models of information acquisition where you have these assumptions are the classic model of Wald with linear cost, where you take samples, and for each sample you pay a cost. And there, standard assumption is that you have a linear cost. So every time you take a sample from the population, you pay $10. And then you solve this cost-benefit trade-off. So there again, right, you're going to have eventually the value of one more sample is going to be very low for you, but maybe the cost is fixed. Another situation where you have similar assumption is when you have normal experiments. So you're performing this normal measurement with normal noise, and the cost is quadratic in the variance or the precision of the experiment. Anyway, this is a standard assumption that is equivalent to this idea of additivity.
Linear in the inverse of the precision, I guess, right? Isn't it?
Yes, I think so. Yes, thanks. And yeah,
I mean, I'm not sure, because you are mixing the precisions. I mean, the expected value. Okay, never mind.
But then the question is, okay, so what's a non-parametric way of...
I thought the linear, the quadratic cost with normal is actually within this Sims thing, right? So I thought anyway. I thought if you, in that special case, that's what it boils down to, which is why people liked it, I thought, this. But anyway, maybe I'm off here.
I'm inclined to say no, because when you look at independent copies of an experiment, entropy always has marginal decreasing costs. But maybe you say maybe the case of normal is a knife edge where you have equality. I will have to double check. Yes. Okay. Oh, I only have 15 minutes left, so I should speed up a bit. The discussion was too interesting. I got lost a little bit. So here's our third property. The cost is find in the probability of success of the experiment. The fourth axiom is a continuity axiom, which I will say it's quite technical. We need to define a distance over experiment, which requires two experiments to be close if the distribution of the signals are close both in total variation and in the moments of the log likelihood ratios. So the axiom is technical, so that's not the best equation, the simplest equation we have in the paper, but the distance is, compared to the usual distance over distributions, is very it's very weak in the sense that it takes a lot for a sequence to converge. So continuity in this metric seems a weak property. Nevertheless, it is a technical assumption, and we don't have an example of a cost function that satisfies the first three properties, but not the fourth one. And so the conjecture here is that this property is redundant. That's what we use in the proof. We know that for two states it is redundant, and we need someone else to look at this and think harder and understand whether this is always the case. So what do they get? These four properties, they give you the following. They give you that the cost of an experiment is a weighted sum of these different terms. So let me, can you see the cursor? Yes, okay. So what is the cost of an experiment mu? Okay, it's the following expression. It involves a part that is just defined in terms of the experiment and a part that is sort of specific to the cost. These beta are parameters of the cost function. So how to read this? Take two states I and j. This expression here is the expected log likelihood ratio between state I and state j when I is the true state. So this is just the KL divergence between mu I and mu j, these two different distributions. So what is the idea here? The idea is that if this KL divergence is large, it means that when the state is I, I'm more likely on average to see realizations that favor I over j. Right? So there is a sense in which a higher KL divergence gives me more information about I and j. And now what do these parameters capture? When beta ij goes up, then it will be more costly to acquire an experiment with a certain level of KL divergence between mu I and mu j. So the important thing here is that these parameters are indexed by the states, right? And what's going to be key for the examples is that this freedom of specifying these parameters will allow us to give meaning to the states, right? A key limit of mutual information, something about on which David, right, has worked on recently, is that the states in that model are devoid of meaning. If you take a certain experiment and now you relabel the state and run the corresponding experiment, the cost will be the same. These beta are instead indexed by the state. So if you have meaning that you want to assign to these states, that can be captured in the cost function. Okay, this seems a little metaphysical, so let me maybe jump to an example. So here's a fun example. Very simple information acquisition problem. You have a state I that represents the GDP of the United States, and you're asking, well, I want to learn this state, maybe up to some level of noise, but I want to know what the GDP of the United States is. And you want to know then how expensive should it be to learn a single digit of this number. So if you are like me and you haven't really taken macro classes ever, you will start with maybe a uniform prior Q between 0 and $40 trillion. So this is your state, this is your prior. And now there are maybe two questions you can ask. One is the state above or below 20 trillion, right? It's a natural question. Here is a really metaphysical question, which is the state even or odd, right? Is the GDP even or odd number? Now, under mutual information, these two questions are equally costly to answer. And the reason, as I said, is because the states don't have meaning. The entropy, Shannon's entropy, is a function that depends on the odds of your beliefs, on the probability that your beliefs are assigned to the states, but does not depend on the states themselves, right? Take a distribution, we shuffle the states, but keep the same probabilities, the Shannon's entropy will remain the same. This is a well-known difficulty in the model. So the cost function that we have in the paper has these extra degrees of freedom, right? Has these extra parameters. Actually can be used to capture something very intuitive that is happening here. So let me define a simple experiment so that we have something to work with. Imagine you want to learn about an hypothesis H, which is a set of states, right? Maybe the hypothesis is that the state is above or below a threshold, is even or odd. And you have an experiment mu, which outputs whether the hypothesis H is true or not, right? So it's a simple binary experiment, and this experiment will be correct with a certain probability alpha, conditional on the state. So this is a binary signal. And now, how does the cost of the signal depend on the structure of the hypothesis H? So when you plug this simple experiment in our model, you get these expressions. So the second part of this expression is something that only depends on the precision of the experiment, and the probability that the answer the experiment gives you is correct. But the first part, which is the interesting one, is something that depends on the structure of the hypothesis H.
Can I ask something about the second part, though?
Yes.
Your assumptions were that independent experiments added up the cost, and then there was something about linearity, and then there was the first one. So
yes.
how did you get the log out of those things? Why does the log pop up?
Why does the log? Well, that's a bit of a mystery. It's a good question. Well, I will have to give you the sketch of the proof to give you a satisfactory answer. Basically, what happens is, what's a good way mathematically to think about adding two independent experiments? A way to do it is to look at what happens to the log likelihood ratios. The log likelihood ratio of two independent experiments turns out to be the sum of the log likelihood ratios of the two individual experiments.
I see. So the additivity pushes you towards this log likelihood ratios.
Yeah, so additivity is pushing you towards thinking of the cost as being additive in the space of log likelihood ratios. So, and that's, in a nutshell, what we show, right, is that your cost will be linear over this suitably defined space, suitably defined variable. Okay, so what's happening here? We have these two ingredients of the cost. So let me give you a very simple parameterization. Suppose theta are integers, numbers, and beta takes this form, is 1 over the square distance between the states. Okay, so the idea then, what is the idea, right? If you take two states that are very close, this beta will explode, meaning that the cost of high KL divergence between the information I get in I and in J will also explode. So the decision maker will try not to learn too much about states that are very close to each other because it's very costly. So, so what happens in this example? Well, if you take this simple parameterization, then the two experiments learning about whether the cost, the state is above 20 trillion or whether the state is odd or even are going to be very different. Because the more the hypotheses intertwine, right? Think of odd and even. It's an hypothesis where for any two states, right, neighboring states are going to be one in H complement. such an hypothesis will make this expression explode. The key, right, when you try to apply these two examples is to decide what these parameters are. And that, of course, is something that is context dependent, right? Because it's something that depends on what is the meaning that we give to these parameters. So the way we interpret them is capturing how costly is to distinguish between two particular states. In the paper, we try to strike a balance between how general this beta can be in the representation, the main representation theorem at the beginning, right? It can be any matrix of positive real numbers. And what we do is to propose a functional form for one-dimensional problems, like the one we just saw, right? That is problems where the states are real numbers. And I will avoid, I will skip you what these additional axioms say. These are parametric assumptions. What they imply is they put light on one parameterization, which is one where the beta between two states I and j is something that depends on maybe a constant and the cardinality of the states, but is given by 1 over the square distance between states, right? So what this theorem does, I haven't told you what these axioms are, but basically tells you what is the extra parametric assumptions I must make for the betas to have this property, as we vary the set of states. So here, let me maybe end with this, which is another fun example to bring our cost function to, which has to do with a different type of information acquisition problems, which are perception tasks. What's a perception task? Here's a simple example taken by an experiment by Dean and Nelig. So you are facing a screen in a lab, and you're shown something like this. So there is on the screen, there's going to be a number of blue and red dots, and you are allowed to stare at these dots for a few seconds before you have to take an answer. Give an answer. The answer is to the question of whether there are more red or more blue dots on the screen you're looking at. So you have to bet on whether the majority of dots is red or blue. And you only have a few questions, so you can't really count all of them. You need to use some strategy, right? Maybe you look at, you divide the set of dots into squares, right? You try to understand for each square what's the majority, then you sort of take some kind of average. Whatever you do, this is going to be a problem where some noise is inevitable. Now, what if we try to model this using our models of information acquisition? We can fit this into a standard problem of information acquisition where the decision maker has two actions, betting on red or betting on blue. The state is the number of, say, blue dots on the screen, goes from 0 to 100, and you have a uniform prior, as you actually do in that experiment. The decision maker will solve then some rational inattention optimization problem, right? You choose what experiment to perform, or equivalent, you choose your distribution over beliefs over the states at some cost C. Now, let's compare two predictions under mutual information and under the log likelihood ratio. So to apply the second one, we need to choose a parameterization. And here again, we have a one-dimensional problem. So we're going to think of the distance between states as being what makes learning hard or easy. Think of a state which is close to 50. This is a state where the number of blue dots is roughly equal to the number of red dots. That should be hard to distinguish two states that are that close. Think of the state 0 and 99. Distinguishing between the two states should be very easy, right? Either they are or blue or red. Under mutual information, the prediction is that in every state, you're going to have the same probability of being correct. So in this graph, on the x-axis, you have the number of blue dots. And on the other axis, you have the probability of answering blue. Under red, you have the optimal choice probability under mutual information. So when the true state is above 50, your probability of answering blue is always some number, say 0.85. When the number of blue dots is below 50, your probability of answering blue is another number, say 0.15. And you have this sharp discontinuity. So the probability of being correct is the same when on the screen there are mostly blue dots as when on the screen you almost have fair equal proportion of the two. So clearly, when the number of blue dots is close to 50, your probability of being correct should be 50, right? So your answer is going to be pure noise. This is almost impossible to solve. But when the state is very close to the extremes, your probability of being correct should go close to 1, right? This is the blue line is a typical finding in these psychometric experiments. And it is also the prediction under our cost function. Here's another way to think of it, the probability of answering correctly under our log likelihood ratio cost function and under mutual information. So disregard this thing here, it has to do with the way we break the tie at 50. Okay, so the idea here is that the message is that these extra parameters that appear in the cost function allow you to have extra freedom, and they allow you to capture something meaningful about the states, not just in these examples, but also in others that we study in the paper. And let me end on this note. And as I see, I am out of time. Thank you for all your questions and comments. Thank you for your attention.
Thank you very much. So now we still have a bit of time for discussion. So first, I would give some time to the panelists in case they would like to make any more comments.
Yeah, so going to axiom number 3, you mentioned that what's it called? Posterior separability implies linearity. Is the reverse direction true? Or do you have a counterexample?
Okay, sorry, I got lost here in the slides. Yes, so so if you have only black hole monotonicity and this one, my guess is that it's not enough to have posterior separability. I don't have a counterexample.
Right. I mean, I'm just thinking that like indifference to randomization over experiments, which is related to what you have here, is equivalent to posterior separability, and I'm wondering if you can combine this maybe like with an axiom like in De Oliveira et al. On the convexity of costs, that perhaps, or maybe that's not even needed, essentially that if you take a randomization over experiments and then you scale them back up by this axiom number 3, that maybe that would be enough for posterior separability. But obviously this isn't the proof, it's just an intuition that there might be something that you checked.
Yeah, so what will be the example in the mathematical analogy in the case of lotteries, right? It's something that is affine when mixing with, say, a Dirac, right? So, it's not a good analogy because there, if you have affinity with respect to a Dirac, then I can use this right over the support of the lottery inductively. Here, you can't do it. Yeah, I don't know. It's a good. I don't have a counterexample, but I guess there should be one.
Yeah, or maybe even if it doesn't get there, maybe there's some intermediate axiom that's weaker than axiom number 2 that gets you it.
Yeah. Yeah, it's possible, yes.
Hi. I have lots of questions, but a lot of them are about things that you didn't have time to talk about, so they're probably inappropriate. But maybe we could talk about interpretation of the betas. So if we had a simple example where, there's binary choice, the agent is picking A or B. We had two states of the world, 1 and 2 that are payoff relevant, and 1 I want to pick A, and then 2 I want to pick B, and any other state of the world I don't care at all. A and B have the same payoff. Then if I had fit this cost function and beta 1, 2 is really low, and assume it's the same as beta 2, 1, then what I would be tempted to conclude is that the agent should differentiate between states 1 and 2 really well. There should be a really high chance of A being played in 1 and a really high chance of B being played in 2. But maybe I'm missing something with the KL divergence, but it seems like that conclusion isn't true because, if I have some other state 3 and I can have different behavior in 1 and 2, then the behavior in 3 has to be different from at least 1 or 2. And so there might be the cost parameters, beta 1 to 3 and beta 2, 3. If these are high, then it's still going to be really costly for me to have this behavior where I'm differentiating in the states 1 and 2.
But if I have more, if these states are mutually exclusive, 1 and 2 are payoff relevant, but then also the other states also must be payoff relevant in a way,
So say there's a state 3 where A and B give me the same payoff. And so in B,
okay.
I don't care at all. Really what I want to do is if it's 1, I want to play A. If it's 2, I want to play B. And if it's any other state, I don't care. And so really what I'm trying to do is, rule out that it's, conclude that it's 1 or 2 or rule out. And then, I don't care. And I kind of ignore all of the other states.
Yeah, I would say, okay, it's a good example. So maybe one can't really presume this sort of IAA property, right? Because, right, what if it's a pin in the haystack problem? So, maybe you have 2 states where the actions are risky, but then you have a million other states where the actions give you the same payoff. But it may be really hard to distinguish whether the state is one where the action is safe versus one where the action is risky. So intuitively, the difficulty between distinguishing between the 2 states should not be independent of how many states are there beyond these 2. So information about beta 1 versus beta 1 and beta 2, 1 shouldn't be enough to, predict behavior. You really need to know, or to write down also what are the beta for the other states. That's at least my reading of the example. Maybe in other situations where something what you're saying also should maybe apply is one where the states as a product structure, right? And then maybe I want to learn about the first coordinate, but I don't care about learning about the second coordinate. And now, what is a useful structure for the betas as we look at, right? As we look at this product space of states, we haven't thought about it. I mean, it seems like a very simple class of problems, but we don't have a ready to go interesting parameterization of the betas there. And there, maybe you want to have sometimes this sort of IAA property. Learning about one dimension should not, the cost of that should not depend on what happens on the other dimension.
Can I ask about the necessary conditions in the paper, or should I maybe wait and allow other people to ask questions about the talk.
The what necessary?
The necessary conditions for optimal behavior.
Yes. So I don't have it on the slides. Maybe let me just say what they are in one line. So take this cost, apply to a discrete choice problem, where you have finitely many actions and states, and the decision maker is solving for the optimal experiments. That's going to be a concave optimization problem. So there are going to be some first order conditions. And in the paper, we derive these first order conditions. I didn't put them in the paper because it's sort of a routine step in sort of these problems. But do you? Yeah,
maybe we give one moment Francesco the chance to ask a question, and then if you want, we can get back to it in the unofficial part.
Sure.
Francesco has been raising his hand for a while.
No, I mean, yeah, it's can you hear me? Yeah.
Yeah.
Now, I was wondering, would it be fair to say that, I mean, so to present what you're doing this way. So people in the past have looked at conjugate models and the experiments in this model have a real world interpretation in some specific context, and they would attach a constant cost or a linear cost to these experiments, and you want to understand in a general sense what the implications would be beyond the specific models, because we need to have robust predictions. We need to our models are metaphors that do not have a real content. I mean, would it be fair to start the presentation instead of axioms, starting it with saying, look, I mean, these are in these conjugate models, these interpretations have very real meaning, but we want to say more in general what is. I mean,
it is. In the paper, we also that's the way we relate to Wald in a way, and to this models, normal experiment.
Yeah, you mentioned normal, then there is beta Bernoulli. I mean, so these are. I mean, it's natural in the conjugate models to think about every draw as an experiment having a cost, and you're going beyond that because you want to have a general model that is robust to specifications.
Yeah, no, it's a fair way. Actually, it's also the way we arrived at this project. You have the Wald model, and there, right, if the cost is linear in the number of samples, or it's linear in the time that you spend observing the signal, then it's clear that what you're assuming is some kind of constant marginal costs. But what if you want to capture that in this non-parametric world where your primitives are not time or samples or just experiments? And this seemed like a way to capture that, a way to go. So yes, definitely, that's one way we got here. That's definitely a part of our motivation.
Thanks.
All right, so should we maybe stop the official part? Let me officially thank Luciano for the nice presentation, and David and Jeffrey for being panelists, and everybody who asked questions. Thanks very much. And next week we have Nathan Yoda, who's presenting